Welcome to worksheet number 15, limits to infinity horizontal asymptotes. This corresponds to book section number 3.4. So in the last few worksheets, we talked about how the graph of the given function can be shaped different ways. We can look at the first derivative, we can look at the second derivative, we can find the max and mean and all that stuff. Today in this worksheet, we'll investigate the shape of the graph towards the infinity. Infinity means like x values and y values. Either x values is huge or y values is big, right? So like towards the end of the graph, like this is where x value is a positive infinity, that way. To the left is when x value is negative infinity. Top is when y value is positive infinity, and then here is when the y value is negative infinity. So I'm looking at the graph in 4 corners. Like if you go up forever, how does the graph look like? And so on and so forth. So let's look at the example 1. F of x is 1 over x. So the graph is given. Graph of 1 over x is like this. As x gets larger and larger, so x is 1, 2, 3, 4, 5, 6. Again, like 7 million. Obviously, we don't have space to display the whole thing, but imagine your graph is going this way, right? So then what will happen to the graph? My graph is this. If you look at the y value, it gets smaller and smaller. It becomes almost 0. But it never actually touches the x-axis. It just stays just a little bit above x-axis, but it gets very close to 0. So again, this is a concept of the limit. So as x gets larger and larger, the f of x, which is the y value, f of x, which is the y, which is the height of the graph, gets closer and closer to 0. And on the other hand, as x gets smaller and smaller, which is a big negative number, so negative 1, negative 5, negative 100, negative million, like over here. My graph is going to go like this. Kind of similar concept. It goes to 0, which is the height of the graph. 0 is here, right? So it gets to 0. So again, f of x, which is the y value, gets close to 0. So what we can say is that limit as x approaches to infinity. Before we look at the limit as x approaches a particular number, here we're looking at x approaching to a negative positive infinity, means look at the values when x is huge and see what happens to the good behavior of the graph at that point. So here we can say it's equal to 0 because of this part, right? So we can kind of define limit as x goes to a certain number. Now we can kind of talk about limit as x goes to negative infinity or x goes to positive infinity and so on and so forth, right? It could be a particular number or it can be infinity or negative infinity. So let's look at example 2. Limit as x goes to negative infinity of 1 over x. Same graph, but instead of looking at to the right side of the x-axis, I'm looking at now left side of x-axis. So that, again, the height of the graph goes to 0. So that one is also 0. Here, limit of x as x goes to infinity. Well, this kind of makes sense. When x becomes larger and larger, what happens to x? Well, it's like it gets larger and larger, right? So as infinity. If you look at the graph of x, let's say f of x is equal to x. There's just a straight line with slope 1 because x is like 1x plus 0. So slope is 1 and then intercept is 0. So this is the graph, right? So if you look at the graph, what happens when x gets bigger? Your graph goes up. So height of the graph gets larger, larger, larger. It goes up. So I can kind of say that it's infinity from there also. All right, let's look at the next property. So this is very similar to the property of the limit as what we talked about in the very first worksheet. So if you have a constant, if you take the limit as a constant, if you add the limit, basically, you can take the limit of each one separately and add them together. When the constant is multiplied, you can do the same thing. Multiplication, division, they're all pretty much the same. Again, like only thing we have to worry about is when you have 0 denominator. That's when you have to do some extra work. Number 6, 1 over x to the sum power. So we looked at 1 over x. The limit was 0 as x goes to infinity. What if it was like x squared or x to the 3rd power or x to the 4th power or whatever? Kind of same thing. So for example, like I can say limit of 1 over x squared, x goes to infinity is also equal to 0 and so on and so forth. The next one, whereas x goes to infinity, 1 over x to the sum power. So for example, limit of x x goes to negative infinity over 1 over x squared is also 0. When you square x, if it's a negative number, x squared becomes positive, this, right? There's a little bit of a little extra information here. XR is defined for all x. So if you have something like limit of 1 over x to the 1/2 power, which is basically limit 1 over radical x, this one, x goes to negative infinity. Like this one doesn't exist because we can't even have a graph, because when x goes to negative infinity, like negative number, you cannot really plug in negative under the radical. You can have negative, so the graph doesn't exist there. So that's why it says when x to the r is defined. But here, x to the r, 1 over radical x, x is not defined for negative values. So this one doesn't exist. The question like doesn't make sense. Okay, let's look at the next one, which is the most interesting one. We have limit as x goes to infinity, p of x, q of x. These are two polynomials. So rational functions is polynomial over polynomial. So it looks like something to the x power, x to the some power, and then x to the something else other power, and so on and so forth. So for example, like x squared plus 2x over 5 plus 5 over like x to the third plus 5x minus 5 or something like that. That will be an example of a rational function. So they have a polynomial on the top, polynomial on the bottom. And we're taking x limit as x goes to infinity. Basically, for that type of situation, the highest power term determines the behavior of the limit. So this is kind of important. Let me highlight this part here. The highest power determines the limit. So basically, you look at the highest power and see what happens. So if the highest power here is larger than that power, basically this will dominate everything. So it'll be like 1 over x. So it'll go to 0. So the limit will be 0 if n is bigger than m. Means the power on the bottom, is bigger than the power on the top, right? And it goes to infinity if the other way around, n is bigger than m, meaning the power on the top, maybe the top is third power and the bottom is second power. Basically, top power will just dominate the bottom, so it'll be just x to the n power, x to the third. So that'll just be the power on the power on the top is bigger than the bottom. And the third case is what if they're equal? What if it's like 2x squared and then like 4x squared? What happens when the power is the same? Basically, they'll just cancel out. So it'll just go to the coefficient. So if it's 2x squared over 4x squared, basically it'll be the same as 2 over 4. So am over bn if n and m are equal to each other. Okay, so if you have a rational function, basically we'll compare the power at the top, power at the bottom. You get either 0, infinity, or a particular number. To find the limit, so that's like conceptually, that's what's going to happen. To find the limit, we divide each term of the rational function by the highest power of the denominator. So denominator, which is the bottom part, right? All right, before we actually look at the example, let's kind of look at, this is for technicality. Let's look at one like a simple case, but with a little twist. The one has a square root in it. Let's look at the first one. You have square root of x squared over x. Isn't square root of x squared, is square root of something square, isn't it just that? So in essence, it's basically x over x, means they have the same power, basically x to the first, x to the first. So I'll just go to this, which is 1. So I know the answer is going to be 1, but I want to show like mathematically why it's 1. So to show the actual limit, I want to divide each term into the highest power of the denominator. So highest power of the denominator is just x to the 1 power. So I'm going to divide by x. I'm going to divide by x. Here we know that if I have like radical 10 divided by 3, if I want to put 3 into the radical, basically I have to do kind of like radical 3 divided by radical 9, which is like this, right? So if I'm kind of forcing, if I'm dividing like a whole number into the radical, if I want to push like 3 into the radical, basically I have to like input it as 9, right? if I did it like radical 3 divided by 3 is radical 10 over 3, they'll be wrong. Because radical 9 is 3, not radical 3 is not 3, right? That's why. So I'm going to kind of do the same thing. I'm dividing by x, so it'll be limit. The bottom part is no problem. X divided by x is just 1. On the top part is going to be x squared over x squared. Again, like I'm dividing by x, but because it's a square root, I'm putting x squared here. Okay, so that's limit just 1. So x squared divided by x squared is 1. Radical 1 is 1. 1 over 1 is just 1. So my final answer is 1. All right. So that's that. Let's look at the second part. Almost the same question. Only difference is that there is a negative. The reason it's a little tricky is because I have a radical and then there's a negative. So for example, if I have like radical negative 3 squared, that's radical 9, which is 3. So that's not too bad. However, number I plug in is negative 3 squared. It wasn't like 3 squared. So radical of 3 squared is 3. So that's easy. Radical of negative 3, the entire negative 3, is also 3. But I thought I'd plug in negative 3. How come I got positive 3? How do you reconcile that? So here I'm going to have to write it as negative of negative 3, right? Because negative of negative 3 is positive 3. So what I'm trying to say is negative 3 is basically the same thing as negative of negative 3 squared. I know it's confusing because negative 3 is negative. This will give you positive. So if I didn't have this negative sign, that'd be kind of wrong, right? So negative 3 is equal to negative 3 squared. We give you positive 3, so I have to have that extra negative. So this is true if you have a negative number, right? So I'm going to use that for this question because here I'm taking x as negative infinity. So basically numbers I'm going to plug it in here is going to be negative. So I'll use that fact. So how do I evaluate that? Kind of same thing. I'll divide both sides by x here. So on the bottom, I have no problem. X divided by x is just 1. On the top is radical x squared. So I'll write x as negative radical x squared because x is negative. So I'm going to rewrite it as negative radical x squared. So that's the part I have to be super careful. So what did I get from there? On the top, I get negative 1. On the bottom, I get negative 1. So it'll be negative 1 is my final answer. So I know it's kind of weird, but answer is negative 1. You can kind of double check. So here, just to verify, let's say plug in like x is equal to negative 10,000 or something like that. So if you have a radical negative 10,000 squared over negative 10,000, right? So on the top you get 10,000 positive. On the bottom you get 10,000. Did I say 10,000? I meant, yeah, 10,000. So it's negative 1. So I can kind of verify that. All right, let's look at the next example. So let's say example 4. Let's look at the first one. It's the most straightforward question. I have polynomial over polynomial. I noticed that powers are exactly the same. 2 on the top, 2 on the bottom. So I know it's going to be 3 over 6 is going to be the answer. But to verify it or algebraically show, I'm going to have to divide everything by x squared. So I'm dividing by the highest term of the bottom. So what I get is, I'm using blue. So limit as x goes to negative infinity, 3x squared over x squared plus 4x squared, x over x squared plus 2 over x squared. On the bottom, I get 6x squared over x squared plus 5x over x squared minus 3 over x squared. So what happens? Here, x squared goes to infinity, so this goes to 0. Because if I look at only this term, power on the bottom is 2, power on the top is 0. There's no x, goes to 0. Same here, power on the top is 1, power on the bottom is 2, so it goes to 0. And here, power is x squared will cancel out, so I get 3. Same for the bottom. This goes to 0. Let me write that down. This goes to 0. This goes to 0. And this x squared cancels out, so I'll just get 6. So 1 over 2. All right. I'm going to have you try number 2. So pause and then work on number 2, and we'll make a number 3. All right, if you're done with number 2, you should have gotten an answer as just 2/3 is the answer for that. Basically, highest power is 3 on the top, on the bottom, sorry. Here is 6, but square root of x6 basically works as x to the 3rd. So I'm dividing everything, each term, by x to the cube to get that answer. Let's look at number 3. Okay, my first instinct was plug in infinity. So this is infinity means big number. Radical infinity is infinity minus infinity. So this is kind of like, I want to make a little comment. If you get infinity minus infinity, again, it's not 0. It's not 0. We don't know that. We don't know what it is. We don't know what it is. What infinity minus infinity is equal to? It could be 0. It could be infinity. It could be positive infinity. It could be a particular number. So further investigation is needed. Same as 0/0. Again, this is, we don't know what it is, right? It's not 1 necessarily. So this is kind of a similar case. Just make another comment. Infinity over infinity, because infinity is not a number. Infinity over infinity, we don't know what that is, right? All right, so having said that, let's look at this. Basically, it's infinity minus infinity. So that means we don't know what it is. I think we saw something like the radical something minus something. Maybe you can try to multiply conjugate. So let's see if that works. Radical 9x squared plus 4 plus 3x. Radical 9x plus 4 plus 3x. So I'm multiplying that in top and bottom. So what I get is limit x goes to infinity. Infinity. A minus b, a plus b. So I get 9x squared plus 4 minus 9x squared. So that's my a. This is my b. A, b. So a minus b times a plus b is a squared minus b squared. This is my a squared. This is my b squared. Right? So that's the top. On the bottom, I get radical 9x squared plus 4 plus 3x. For the top, I can cancel this one out. So limit 4 over radical 9x squared plus 4 plus 3x as x goes to infinity. Okay, so then on the top, we get 4. On the bottom, the power is 1 because power is 1. Top because power is 0, so it goes to 0. Yay. All right, let's look at number 4. Number 4, there's no like formula or anything, but I know the cosine, so limit of x goes to infinity of cosine x. I know the graph of cosine x goes like this. Cosine x. It just oscillates, goes up and down, right? So what happens to the graph when x goes to infinity? It does not approach one particular number. It just goes up and down and up and down. So the limit doesn't exist. So this is purely just by looking at the graph of the cosine x. The last one here, limit as x goes to infinity, cosine x over x. I know the bottom goes to infinity. Top doesn't exist. So, but I know it's bounded, right? So it's bounded. So I think we can use a squeeze theorem. So we can kind of do the same thing. Cosine x goes from 1 to -1, right? So -1 over x, cosine x, 1 over x. I'm dividing like this, right? We know that this goes to 0. We know that this goes to 0. So by squeeze theorem, so we can kind of do the same thing. Theorem. The middle one goes to the 0. When we have the squeeze theorem, it has to be like a particular number, but it works for infinity as well. So by squeeze theorem, number 5 goes to 0. So let's go to 0. All right, let's look at example 5. It says use the intercept and asymptote to sketch the graph of this. So this is again rational function. I have a polynomial on the top, polynomial on the bottom. for intercept, we have the x-intercept, which is the place where a graph goes through x-axis. So if graph goes like this is x-intercept. If graph goes like that, that's x-intercept. That happens when y value is equal to 0. So this is plug in y is equal to 0. And y-intercept is basically the other way around. Plug in x is equal to 0. So I think y-intercept is easier to find. So plug in x is equal to 0 to find the y-intercept. Plug in 0 here, 0 here, 0 here. So 0 plus 1 over negative 2. So y is equal to negative 1/2. So 0, negative 1/2. 0, negative 1/2. Somewhere here. So I don't know how the graph looks, but it basically passes through this somewhere. For the x-intercept, let's plug in 0 for y. So plug in y is equal to 0. So 0 is equal to x squared plus 1 over 2x squared minus 3x minus 2. When we have a rational expression is equal to 0, the bottom is never 0 because it's not defined when the bottom is equal to 0. So the only time this is 0 is when the top is 0. X squared plus 1, x squared plus 1 is equal to 0. That means x squared is negative 1, which is never the case. X squared cannot be negative 1. X squared cannot be negative. So there's no x-intercept. So we only have y-intercept, no x-intercept, right? So, all right, asymptotes. Basically, this is when x goes to positive infinity, when x approaches to negative infinity. I want to see what happens to the behavior of this function. So limit of x goes to infinity of f of x. Let's say this is f of x, right? I have the exponent on top is 2, exponent on the bottom is 2, basically. So the limit is going to be 1 over 2, right? So 1 over 2. Limit as f of x as x goes to negative infinity. Basically same thing. Power is the same, so it goes to 1 over 2. So that means 1 over 2 is right here. 1 over 2 is right here. So again, the graph is going to basically look like, I don't know if it's going to come this way, but graph is going to look like this line. If I go out this much, the graph is going to basically look like this line and this line. So this is going to be my horizontal asymptote. Horizontal asymptote. So horizontal asymptote is when we take the limit as x goes to infinity or positive, negative infinity or positive infinity. The vertical one is when you have 0 denominator. So that's our candidate, and then see what happens to that. So when do we get 0 denominator? Well, that means 2x squared minus 3x minus 2 is equal to 0. Again, you can factor like this, 1, 2. So 2x plus 1, x minus 2 is equal to 0. Let me double check. 2x squared minus 4x plus 1, so that's negative 3x minus 2. Okay. So that means x is equal to negative 1/2 and x is equal to 2. So when x is negative 1/2, let me draw the line here, vertical line here. And when x is equal to 2, so there is my possible asymptotes. So let's see, I might need a little more space, but let's look at 2 first. Limit x goes to 2 from the positive side, right? So here I'm gonna rewrite. So when I plug in 2 here, you're gonna get 0. So that's 3 over 0. That's gonna be infinity. So I have to decide if it's gonna be positive infinity or negative infinity. So no, top, I'm gonna get 5 on the top when you plug in 2, right? How about the bottom? I'm plugging 2 from the right hand side. So this is when graph is approaching this way. Is it gonna go up like this, or is it gonna go down infinity, negative infinity? So I'm gonna have to decide. Plug in like 2.1, that's positive. That's positive. So positive times positive is positive. So this is gonna be 0, but it's gonna be like a positive 0. So this will be positive infinity. So that means my graph is going to go up. So it's going to go up like this. That means my graph is going to go like this, right? And how about limit as x goes to 2 from the left? So here, like plug in like 1.9. So 1.9, plug it here, is going to be a positive number. 1.9 minus 2 is going to be basically negative. So positive by negative is negative. So 5 over 0, but it's like negative 0. So that would be negative infinity. So what does that mean? I'm approaching negative 2 from the left-hand side. So it goes down to negative infinity, right? I can kind of do the same thing for negative 1/2. And you can see, I'm not going to work out everything, but basically the graph is going to look like this. Right? So I have vertical asymptotes here, and then horizontal asymptotes here. So let me circle, let me box this. Horizontal asymptote at y is equal to 1/2. And then I need more space. And then let me just write it here. Vertical asymptote at x is equal to 2, and then x is equal to negative 1/2. All right. So I have one more, like a kind of summary of what we did. Vertical asymptotes has vertical asymptote x is equal to a when limit of f of x as x goes to a either plus or x goes to a minus, either is plus infinity or minus infinity, right? So your graph goes to the infinity or negative infinity according to this vertical line, right? So if that happens, that's the vertical infinity, a vertical asymptote. For horizontal asymptote is when the limit of f of x goes to infinity, always a number, and then same here, x goes to negative infinity is some number. So then I can say y is equal to L is a horizontal asymptote. In this case, x is equal to, for the previous case, x is equal to a is a vertical asymptote. So that's vertical line at a. This is y is equal to L, so horizontal line at L. Slant diagonal asymptote is when the limit of f of x as x goes to infinity, or limit f of x goes to negative infinity, behaves like ax. So not a number, but so basically the power on the top is 1 more than the bottom. If powers are the same, like this question, power on the top and power on the bottom are the same, right? So when you take x to the infinity or negative infinity, you're going to get a number. So you get the horizontal asymptote. If the power on the top was 3, that means it's going to basically act like x over 2, which is just straight line. So in that case, your asymptote is going to be like a diagonal asymptote. All right, I think that's it for this workshop. Oh, we have some here. I'm going to have you finish the next 2 just by looking at the graph and figure out where the asymptotes are. Okay, and the answer is going to be, so I'm going to have you pause and look at these graphs and figure out the asymptotes. So if you figure it out, the answer should be in vertical asymptote here. Does not exist, right? Does not exist. Horizontal asymptote, I see this one. Right? So y is equal to 1 is going to be the horizontal asymptote. The next one, vertical asymptotes. I see one right here, I think. So vertical one, that's x is equal to 3 over 2 or 1/2. And then horizontal asymptote, I feel like I see one like here that goes to the right. So possibly like 1/2. And to the left, it goes like here maybe. So y is equal to -1/2. All right, we're done with this worksheet.